Welcome to Regulated Power Supplies, Part 7. So here is our fixed voltage regulated power supply that we've been developing over since the beginning of the series. And it's great, it works awesome, but it only does 1 voltage at a time. So the next version or next step in this evolution is to build a variable voltage power supply. So here it is. Drink in its awesomeness. We're now going to be able to control our voltage on the output with the RV1 potentiometer. So don't freak out. It's very similar to the previous version. We're just going to add a few things. You can see I added a bridge rectifier. That's going to help get our ripple down. We also, you can see that we still got our Darlington pair. You can also see there's a control branch R1 and some diodes, and R2's in there doing something, and 3 and 4 are doing something, and we're going to figure that out. Okay, so the first thing we're going to do is try to decide, like, what do we want our voltage range to be? What are our constraints here? So we know that in order for the Darlington pair to work right, we need to make sure we've got at least 2 volts VCE on those transistors. We need some. We don't want to bottom them out. Okay. We also know that the minimum V out, if you can look at the base of Q3 there, the new transistor that we set to the circuit. Imagine if that base of that transistor was tied all the way to the top and R3 was 0 ohms, or R3 was not even there electrically. The voltage on the base of Q2 would be your minimum voltage out. We're going to get into that a little bit deeper in a bit. So in order to determine, when the capacitor is fully charged, the VC1 max, it's going to be just like the formula before, but now that we've got a bridge, we're going to subtract off 1 more diode drop. So we end up with the secondary voltage subtract 1.4 volts, peak in peak. And so that leaves us with a VC1 max of 41.0328 volts. Okay, and so we know that our voltage range for R3 and R4, setting our voltage range, we're not going to be able to go above what the max voltage is at that cap. And really, we also know that that cap is probably going to discharge a little bit. It's going to help that we added the rectifier in. But we need to keep that 2 volts minimum on the VCE of Q1. So in order to calculate, that's what's going to determine our maximum. So we know our maximum needs to be somewhere less than 41 volts. Really, it needs to be less than 30, 39, or 38, right? Somewhere less than that to keep the 2 volts on the tip 41. Okay, so now the minimum side, that voltage, if we look at that transistor Q3 and we Kirchhoff just from the base of that transistor all the way to ground through the diodes, we see that we get a VBE and then all 3 of those diodes added up. So we know that there's 2.8 volts sitting there. So our minimum voltage that we could ever go down to, and while we're still regulated, would be 2.8 volts. So let's pick somewhere in there where we'll be able to work and solve for an R3 and R4, and let's pick a range of 5 volts to 35 volts. 35 volts gives us plenty of VCE left over for Q1, even if C1 discharges a little bit. And then the 5 volts gives us If we wanted that to be, we could go all the way down to 2.8 volts for that minimum, and then we just get rid of R3. But if we want to pick a minimum and then adjust for that or calculate for that, let's pick a value of 5 volts. So we're looking at designing this thing for 5 volts to 35 volts. Okay, so we're going to do a real world design as though our customer said that they want a power supply that runs 5 volts to 35. So what we're going to do is we're going to write two loop equations through that branch, that R3, the variable resistor, and R4 branch. The base current on that transistor is going to be pretty tiny, so we don't even really need to worry about that right now. Let's just write a loop equation straight down through that branch. And if we imagine our potentiometer being adjusted to both extremes, one where you would adjust pin 2 all the way up to pin 1, and then the next extreme would be when you adjust that all the way down to pin 3. And you can imagine the way that I remember it is like if I move you got 2.8 volts sitting at that base of Q3 all the time. So if you move that potentiometer up and you look at the resistance from that point to ground, you can see that you've got the 1K and the R4. So to me, that's your maximum resistance position, but your minimum current position. So that's going to determine your Vmin adjustment. Then likewise, if you move it all the way the other direction, and now your 2.8 volts is only sitting across R4, that's going to give you your maximum current, right? 2.8 volts divided by something less than, it's going to give me my max current situation, and that is going to determine my Vmax scenario. So you can see right there, the equation's right there in that loop, and you can just pull the equation out of that branch right there. So your Vmin is actually equal to the voltage at the base of Q3, which is the 2.8 volts, divided by, if you adjust that all the way up to the top, it'd be RV1 plus R4. And you can think of that, a voltage divided by resistance, as a current. And if we want to find the voltage of the total branch, we're going to take that current times the total branch resistance, which is the R3 plus the 1K variable resistor plus the R4. That's where that equation comes from. Okay, now we're going to set that equal to, instead of setting it equal to 5 volts for our minimum, let's go ahead and set it equal to 4 volts for our minimum, because if we're going to actually build this, right, we want to make sure that we can achieve 5 to 35. So if you achieve 4 volts to 36 volts, for example, you have achieved 5 to 35. But if you calculate everything out for 5 to 35, and then you go and build it, and it comes up 5.1, 5.2, and the customer can't get it all the way down to 5, right? Or all the way up to 35. Then you haven't really met the demand for the power supply. So it's okay to go, when you build, to run a little bit outside of the 5 to 35, but it's not okay if you can't get to your specifications. So we're going to set that equal to 4, and then we're going to leave that equation alone for now. Put in our knowns, so we know it's 2.8 volts. We know our potentiometer was given as a 1K. And if you had a different potentiometer, you can just do this. It's the same calculations, just put that potentiometer value in there. And then R3 plus RV plus R4. Sometimes that's just the R. You could call that your RT also, your branch total resistance. Now, Vmax, we're going to do the same thing, and we're going to give ourselves a volt padding on this side also. So we're going to say 36 volts is equal to VBQ3 divided by R4, the potentiometer all the way at the other extreme. That gives me my max current. My max current times that total resistance in that branch gives me the voltage. Okay, so we're going to do an extra math step here, and essentially we're trying to solve or get the R3 plus the 1K plus the R4, which is common in both equations, to one side of the equal sign. for each equation. So you can see the math there. We're just multiplying on the first one. You're just multiplying both sides by the reciprocal of the fraction, and then that cancels out the fraction on that side and gets the RT part all by itself. And we're going to do the same thing on the other one. Okay, here's where the cool part of the math comes in. We've got both these equations set equal to R3 plus 1K plus R4, right? So if both those equations equal that, then they also equal each other, if that makes sense, right? If they're equal to R3 plus 1K plus R4, then you should be able to set, and this is what I call super substitution method. So now I can take the 4V side of the equation and set that equal to the 36V side of the equation. And the beauty of that is now I've got only one variable in that equation, R4. And now I can just go through and do algebra and solve for R4. And I've got a R4 equal to 125 ohms. Okay, so now what we've got R4, we're going to punch R4 back into either one of those original two equations and then solve for R3. And for me, I've got a R3 of 482.143 ohms. All right, so I looked up in Mouser, and you can get a 125 ohm resistor. I think it was 20 something cents, a little more expensive than normal. And then 482 though is not a standard value. I found a 475 ohm resistor, both quarter watt. And now you're going to see we're going to take those numbers and put them back into the two original equations and solve for Vmin and Vmax, and make sure that now that I've moved my resistors to standard values, that I haven't deviated or gone too far or broken my 5 to 35 range that I'm looking for. You can see when I do the math, I get a new Vmin, an actual Vmin now of 3.98 volts calculated with the standard values, and a Vmax of 35.84 volts standard value. So you can see that I'm still able to get from 5 to 35 volts. Okay, so we've got R3 and R4 in the circuit, 475 ohms and 125 ohms. Our actual, looks like our variable voltage is going to go from 3.98 volts all the way up to 35.84 volts. 35.84 volts on the output gives me plenty of, basically I can have more ripple, I can have a smaller cap now, and we'll recalculate all that stuff, but we've got plenty of VCE on those on the Darlington pairs, because we've got 40 volts sitting on the other side. And then here is the parts for Mouser, the R3 and R4 that I looked up. It looks like it's 26 cents for that 125 ohms. And you can mix and match those resistors in those positions if you have standard values already on hand, or if you want something a little bit cheaper, or if you wanted, even if you had a 120 and you wanted to go in and recalculate the numbers, just make sure that you don't violate whatever your specification is for your original range.